This is Lecture 9H for Calculus 2 on the solution of the elementary model of population dynamics. So we look at the first population model. This is a model that says the rate of change of the population is proportional to how big the population is. Okay. Now we study methods such as using separable equations, integrating factors, Euler's method, but there's another method that's commonly used to solve differential equations, and that is pattern recognition. If you can see what the solution might be, go ahead and try it out. And always try out exponentials first. They're pretty popular in differential equations. Okay, so now what I'm going to do is look at an exponential. If I had some exponential a e to the kt and I took its derivative, I would get k times a to the kt. I would get the original function back multiplied by k. In other words, I would have just exactly this situation here. So I'm going to set p, I'll say p equals, well, I'll use the c there, I can use a, e to the kt. I can put this in the equation and solve it, which is exactly what was done here. But you'll see I will satisfy the differential equation by p equals a e to the kt. So now I have a solution, but I have a constant in here, and I would like to evaluate the constant. Let's do it by using the initial condition that p at time 0 is p naught. Okay, and this is pretty trivial. I'm sure you can do this. So if you have p at 0 equals p naught, but I know that is equal to a e to the, and I'm going to evaluate it at 0. This, of course, is 1, so I end up with a. So the constant a is equal to the population at 0, at time 0. And here's the solution for that differential equation. When we looked at this equation graphically, we found that it had only one equilibrium solution, and that was p equals 0. But let's look now at another case. Let's look at what happens when k is different. Right. Let's say we start off here with a population of 4 somethings, okay, and let k be greater than 0. That means the birth rate exceeds well, you can't even see that now, can you? Maybe you can. The birth rate exceeds the death rate up here in this region, greater than this dashed line right here, which is not a solution at all. It's just a dashed line. Okay, so if k is greater than 0, the birth rate exceeds the death rate, the population will be increasing, and you can see on these curves that it is increasing. Now, how fast it increases depends on k. If the birth rate is much greater than the death rate, it will be perhaps along this curve. If the birth rate is close to the death rate, it might be a very slow growth. Okay, now let's look at the other situation, that if the death rate exceeds the birth rate, now k is 0, k is negative, and this is a decaying exponential. It's a decaying exponential for k less than 0, for birth rate exceeding death rate. And you can see how these curves, this would be k less than 0, they decrease, well, they don't go below 0, at least not to my knowledge. And how fast they go down depends upon k. If your death rate is really great, you'll be over here. If the death rate is approximately equal to the birth rate, you'd have a very slow decay.